welcome or welcome back to my channel. So in my channel today, Classic Biology, we will be discussing the Vesper theory. So Vesper theory is a really interesting topic from chemical bonding, and along with Vesper theory we will be discussing valence bond theory, molecular orbital theory, about hybridization and much more, many concepts we will be discussing today. So overall for the NEET preparation, so this video is more than enough when it comes to chemical bonding. So just like this, I am planning to post for all the chemistry chapters a one shot quick lecture, so please keep watching. Now let's get started. So first, if you talk about what is Vesper theory, you can see that these two people called Sidgwick and Powell. So in the year of 1940, what they did, so they took electron pairs, and you see electron and electron, so they are undergoing some repulsion. And it is also said that when there is a bond pair, like for example, carbon is bonding with oxygen, or nitrogen is bonding with oxygen, whatever it is, there is some bond pair, right? So that bond pair repulsion is there, right? It is comparatively lesser. So that repulsion will be lesser because there will be an attraction only towards the bonds, and lone pair is there. Definitely there will be a huge repulsion between the lone pairs, and when you take a lone pair bond pair, kind of an intermediate repulsion will be there. So this repulsion order is very important, and this question was asked in NEET 2016. So now this tabular column is really important. Many questions can be framed regarding the geometry and the shape when you are given this general formula. Okay. So main molecules we will be discussing. You have to remember this, there is no other go. So if you take BF3, so for BF3 both geometry and shape will be trigonal planar. Now this is simple because both are same only. But if you consider, and for example, NH3, now this is also very important. Generally if you draw for NH3, you will get N in the center, and then you will have 3 hydrogen like this. So this NH3 is tetrahedral geometry, and the shape of which is trigonal pyramidal. So NH3 has this trigonal pyramidal shape along with this tetrahedral geometry. And if you take this water, H2O, the shape of which is bent, and geometry will be tetrahedral. And if you consider this SO2 or O3, the shape of which is bent, just like water, here also you have the bent shape. But the geometry will be trigonal planar, but for water the geometry will be tetrahedral. So that is also one example. And you can generally see, so this is the molecule type, and here you have the examples of those molecules. So you can just generally look at the geometry and the shape. And here also if you observe, you have PCl5. So it is both trigonal bipyramidal and trigonal bipyramidal. Now I'll be marking star, okay, star compounds. Those star compounds will have both, same geometry as well as same shape. So if you see BeCl2 and HgCl2, I will put a star, which means that both geometry and shape are linear. And if you take this tetrahedral, the CH4 and NH4, okay, methane and ammonia, that will also I'll be like putting a star. And then you can see this trigonal bipyramidal, PCl5, I'll put a star. So then octahedral, SF6, okay, both it is octahedral. So these stars alone, without exception, please just remember it, because it's very easy. Both geometry and shape are the same for these. And other than that, if you see, I will put double dash, so these compounds are also important. And if you see, H2O will have bent shape, tetrahedral geometry. If you see, NH3 will have trigonal bipyramidal, trigonal pyramidal and tetrahedral geometry. Then if you see SO2O3, bent and trigonal planar. Okay, so these and all we have studied. And even if you see BF3 is trigonal planar. So this also you can put a star. So we have covered almost the important topics. If you want, you can just have a look at this, like some unique shapes. If you see seesaw shape, SF4. So these are some little bit unique things. So from this table, 2022, 2021, 2020, 2018, 2017, 5 years, they have asked questions just from this table, like the geometry, the shape and the examples. That's it. So maybe this year also we can expect a question from this. Okay, so this Vesper theory, it helps us, it proves us all of this, but okay, it has some applications also. Okay, so it is going to give us the geometry and everything, as you can see. So if you take the compounds using this Vesper theory, we will be able to find the geometry of those molecules. Okay, but theoretically if you see, you can't like draw and explain it, but generally you can just obtain these geometry. And then there are some main postulates of Vesper theory. So in this Vesper theory, how many ever electron pairs are there, depending on that only the shape of the molecule will be. You know, these shapes that you can see over here, this is only because of the electron pairs. Okay, whether they are bonded or they are lone pair, that doesn't matter, but only because of these electrons these shapes will be differing. Okay, and you can see that if you take pair of electrons, since they both are negative, okay, they will be repelled, they will be repelled, they will be repelled. Okay, and then you can see that these pair of electrons, they will try, they will try to maximize their distances, that is they will try to be as far apart as possible as to minimize this repulsion. Now if they are closer, there will be more repulsion, but if they try to be as far as they can, then they will be able to reduce the repulsion. Now that is something they do, so electron pairs do. So this Vesper model, it is explaining all of this. It is also applicable to any structure, okay, or any resonating structures also. So this is just some brief introduction about Vesper theory, that is enough to learn, and then this table which is really important to learn. And then we have some limitations also, and some applications also. So all of that we have in Vesper theory. And then if you see this valence bond theory, so this was developed by Pauling, Hitler, London, so and so. And in this basically you take two atoms. Okay, whenever you take two atoms and you bring them, you approach them together, there will be attractive as well as repulsive forces between these two atoms. Now suppose if attractive force is more than whatever repulsive force is coming, then obviously they will come closer. Now repulsive force will try to put them opposite to each other, and they tend to move back. But here attractive force is more than the repulsive force. Attractive force is more. So when attractive force is more, they will come to close, they will come closer to each other. Okay, so that is one application. And then you can see here, suppose if you observe, you have H and H. Now these two H atoms, they will get together and they will be forming this H2 molecule. Okay, so atoms, they are bonded, and when they are getting bonded, there is some energy that is released. Now this is bond enthalpy, which is for this H2, it is 435.8. so whenever these atoms are set, they are said to be bonded, and at that time there will be some energy that is released, and that is bond enthalpy. Now suppose you would have seen all of this, right? So you have one p orbital and then you have one s orbital. So when they are getting closer to each other, obviously there will be some kind of overlapping. Now that is what they are trying to say here. And suppose I have like more overlapping, then it means that stronger the bond is formed. Okay, so and also this valence bond theory, it is explaining about the shape, the directional properties, and how much overlap is seen here, what is hybridization, everything we are getting understood by this valence bond theory, which is quite different from the Vesper theory. So according to Vesper theory, we are able to find the geometry, but here valence bond theory, we are able to find the shape. Now that difference and if you see the type of overlapping and the nature of the bond, there is sigma bond, which is just a head-on overlap, okay, like SS or SP or PP. Okay, just a normal head-on overlap, sigma bond. Okay, and then if you see pi bond, so in this pi bond, the axes are parallel and perpendicular. So just normally like this head-on overlapping means, then that will be under the sigma bond. But when they are either parallel or when they are perpendicular, all that will come under the pi bond. Now in the case of sigma bond, the overlapping will be maximum, and it is also stronger because there is a head-on overlapping, so obviously it has to be stronger, right? And it is occurring in a larger extent. Okay, but if you take a pi bond, since it's either parallel or it is either perpendicular, you can see that the overlapping will only be less, it will be only for a small extent. So if you also take like many multiple bonds are there. So pi bond is formed in addition to sigma bond. So first you count the sigma bond, the rest of which will be pi bond. So all of this is like whatever we have learned in the previous classes. And also this is quite important. If some molecule has this sp hybridization, it has the linear shape. sp2 hybridization, trigonal planar. sp3 tetrahedral. sp3d trigonal bipyramidal. Whether it is sp3d2 or d2sp3, both are just the same, like, but actually they won't be the same. I'm just telling to remember, like exactly the formulas are just the same. So octahedral. And if you take linear is obviously 180, they will be straight. Trigonal planar or something like this, okay, which is 120. And octahedral is like 90. This will be 90 or 120, it depends. And tetrahedral is obviously like this, so it is basically 109. 0.5 degrees. Okay, and the examples of the compound, obviously you know tetrahedral shape CH4 has, so that will come under sp3 hybridization. Now this is also a quick way. If you want to find the shape of the molecule but you know its hybridization, you can just quickly you know do this. They just gave some general points regarding hybridization. So if you want to find you know the shape of many polyatomic molecules, so polyatomic molecule mean they're made up of many you know different types of atom. So then regarding this hybridization, they have given some point. It is basically intermixing of orbital, yes, and they will have different energy. Suppose I take s orbital, I take p orbital. Now this hybridization is basically this overlap or intermixing. Now what you have to understand here is that maybe s orbital will have different energy as compared to a p orbital, so they will try to redistribute their energy. Now once they try to overlap here, their energy will try to be you know distributed equally, okay, and thus we will be getting the hybrid orbital. Now this new orbital where this energy is redistributed, the final orbital that I get will be the hybrid orbital, okay, and you can see that, okay, number of hybrid orbital will be equal to atomic orbitals. How many atomic orbital you consider, that many hybrid orbital you will be having, okay, and these hybrid orbital, they will be having the same energy and shape. Now just now I told you they try to you know redistribute the energy, so obviously they will be having the same energy and shape, okay, they will be equivalent and they are more effective, okay. So they are just some general points are given here, and they will try to have a stable arrangement such that they will have a minimum repulsion, okay, and whatever orbitals that are present in the valence shell are only generally hybridized, you know easily for an atom. If this is you know the nucleus and surrounding that there are many shells, whatever is in the valence shell, now that will be able to easily participate in the hybridization because it's outside, it's so easy, right? Now more than what is inside, if inside has to go, then it needs a lot of energy, and that is really you know very difficult process. So whatever is in the valence shell is, it can easily participate in the hybridization, so they are basically you know more hybridized. And you know as I told, equal energy, equal shape. Now all of this, just pay attention to that. And also you know it is not necessary that only half filled orbitals can participate, you know even if an orbital is fully filled, it can still take part in the hybridization. And now there is also another theory called molecular orbital theory, which was developed by this Mulliken and Hunt. So basically the electrons are present in many orbital called atomic orbital. Now these atomic orbital will combine to form molecular orbital, okay. Atomic orbital will have one nuclei, but molecular orbital will have more than one nuclei, and this number of molecular orbital formed is basically equal to combining atomic orbital. So you take two atomic orbital and they are combined, okay. So how many molecular orbitals will be formed? Two molecular orbitals will be formed. So one will be bonding, the other one will be anti-bonding, okay. So the bonding one will have the lower energy and it will further you know have high stability. And then they have also given the electron probability distribution is given by this orbital. So the orbital are filled based on this Aufbau principle, Pauli principle and Hunt principle. I will put a separate video based on these three principles alone, okay, because these are really important and the question can definitely be asked about you know which option is violating this Pauli principle or something like that, you know they can be asking this. So definitely I will put a separate video for just this alone. And then according to wave mechanic, you know this wave function, right? So this represents the amplitude of the wave. I hope you know that already. In atomic structure and all you would have studied. So from this Schrodinger wave equation, just now I told you. So from this Schrodinger wave equation, you can obtain this wave function. Mathematically, if you want to define it, you can just define, you know, either addition or you can define it as subtraction of wave functions of individual atomic orbitals. And then you can take, you know, the molecular orbital, this is sigma and this is sigma star. So they have just given you generally, and this question was asked in 1990 AIPMT. And then you can see that this is your wave function, okay. And anti-bonding orbital will have higher energy. We have just seen now. So this wave, this is a wave function of A, okay, and this is the increasing energy. So here the bonding orbital will have lower energy. So this is the molecular orbital, this is the bonding orbital. So in molecular orbital there will be minus sign, in bonding orbital there will be plus sign. And then you can see that here it will have the lower energy. There is basically electrons that are bonded here. And the electron density in this is located between the nuclei, okay. So the repulsion will be very less in this bonding orbital, okay, while as in the case of antibonding, you will not have much repulsion. So here within the nucleus itself, the two electrons will be held closer, thus there will be more repulsion here, okay. But if you consider this molecular orbitals, you can see that there will be, very less repulsion, because this, most of the electron density, they are located a bit away from the nuclei, okay. So that thus there will be a less repulsion. Now that point also you have to understand. So this has the lower energy because it has more repulsions, because the electrons are closer in a nucleus. But here if you see, now this one will be having the higher energy because it will have less electron, as the electrons are placed a bit away from the nucleus. I'm sorry. And also there are some condition for the combination of atomic orbital. So the linear combination of atomic orbital, in order to form this molecular orbital, they take place in many steps. So the very first step is the atomic orbitals have to combine, okay. So and when they are combining, they must have some same energy. So only when they have same energy, they can combine. Now these atomic orbitals which have combined, they have the same symmetry, okay. And the combining atomic orbital, they overlap to a maximum extent. And then you can see generally some bond order related questions are there, okay. We will go to that as well. And if you see, they have given you about the sigma, pi and delta. Sigma are symmetrical and pi are not symmetrical, okay. That point you have to understand. And internuclear axis is taken on z direction. Then they have given you a pi bonding MO molecular orbital has electron density above and below the axis. So in a pi bonding, you will have electron density, like this, both above and below this axis you will be having. And then this is the increasing order of energy. It is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, okay. And then it is not sigma again, there will be some pi over here as well. So pi 2px, which is kind of equal to pi 2py, and then you have pi star 2px, that is same, almost similar to pi star 2py, which is less than sigma star 2pz, okay. Now this is the very important order, and questions can be asked from this as well. So with this order only, you will generally be able to find the bond order. Now the important feature of this order is that the energy you have to remember. Energy of sigma is greater than energy of pi of x is greater than energy of pi of y, and the distribution of these electrons in these various orbitals, and that is how electronic configuration is generally formed. So in all of these orbital, how will there be distribution of electron? Now that is what exactly we study in electronic configuration, isn't it? And then if you see stability, the molecule will be stable if the bonding electrons are more than antibonding electrons. It will be unstable if bonding electron is less than antibonding electron. And bond order formula is 1/2 of the distance between the number of electrons present in bonding and non-bonding. So this difference, half of it, okay, that is bond order. And if the bond order is positive, it means that the molecule is stable. But if it is negative or 0, it is basically unstable, okay. And suppose some cases, this is little hard to believe, but there are some cases where bond order comes in integral form. So in such cases there might be single, double or triple bond, okay. And what is exactly bond order? So bond order is like measure of the bond length, okay. There are two atoms. What is the bond length? That is bond order actually. The bond length will decrease. If bond order is increasing, bond length will decrease. And if all the molecular orbitals are doubly occupied, then that will be diamagnetic. Now this is also simple, like all the electrons are paired, there is no unpaired electron, that will be diamagnetic, okay va. So adukapra vandu if there are electrons which are unpaired, okay, like this, so then that will be paramagnetic, okay, in the case of O2 molecule. And then final topic that we have right here is hydrogen bonding. So what is a hydrogen bond? Okay, so it is like a normal force. You have hydrogen and then you have some other electronegative atom, maybe fluorine or oxygen or nitrogen, whatever it is. So basically that attractive force which is acting between these two, okay, that is hydrogen bond. So hydrogen bond can be defined as the attractive force which binds the hydrogen atom of one molecule with the electronegative atom, that is either fluorine, oxygen or nitrogen of another molecule. So this hydrogen bond is like a bridge between these two atoms, okay. And then you can see it is like a dotted line. You can put it like a dotted line But if you take a solid line, then that is a covalent bond. Now that is different, okay. So hydrogen bond, you will use this dotted line. And this, hydrogen bond, it depends on the physical state. How much hydrogen bonding has been occurred. That depends on the physical state of the compound. So if the compound is solid, then there will be maximum bonds, right? Because it is tightly, the atoms are like tightly or closely packed to each other. So there will be, maximum bonding. So it is maximum in the solid state, whereas if you consider the gaseous state, the bonding will be minimum. And then there is also difference between intermolecular hydrogen bond and intramolecular hydrogen bond. So two molecules of same compound that is intermolecular hydrogen bond. Okay, intramolecular means hydrogen bond with electronegative atoms. Okay, hydrogen with electronegative atom. Okay, let us say HO. So that will be intramolecular, but intermolecular means two different molecule. Okay. So and some extra points, okay, so these are some tips or tricks that can be asked in the examination. So maybe while studying this you will be able to answer some previous year questions also. So generally if you want to find hybridization of something, okay, so then you can use this formula. This can look a bit complex, but you would have already studied this. If you properly check, you can remember this. Actually it is half of number of valence electron, okay. So there is a central atom. For example, there is H2O. Oxygen will be the central atom, surrounding which 2 hydrogen is there. So what is the valence electron of oxygen? That, okay, number of valence electron of central atom. That number you have to take. Plus, how many monovalent atom? If hydrogen, only hydrogen or hydrogen or chlorine like that, only monovalent atom, how many are there? You have to take. HCl. How many monovalent atom are there? Like that you have to consider. Okay, you shouldn't just consider blindly, how many atoms are there. NH3, 3 monovalent atom. Like that you have to consider only the monovalent atom. Just, whatever atoms are surrounding the element or the central atom, you shouldn't just consider everything. So plus number of, monovalent atom surrounding the central atom minus cationic charge. If there is any plus charge, you have to minus it. Okay, you have to subtract the charge on the cation. If there is some positive charge, okay, this is cationic charge, you have to add it. Okay, that's it. So this formula will help you to find out the hybridization. And then if you see water has lowest molecular weight among all the hydrates, and then it has highest melting and boiling point. Now this can be very well asked. So they might give you the other hydrates and they can ask you H2O, this oxygen hydrate, this water particularly, it will have the highest melting and highest boiling point. And also this can seem a bit confusing. Ice actually has less density than water. Ice, that is why it is able to float on water. Okay, ice is like not getting submerged, right? It is able to float on the water. That is because it has less density than water. And if you see amides, amides, right? So amides, they have high melting and high boiling point. And then salicylic acid, now that is a stronger acid. This is also an important point. And then this, if you take this order, para greater than ortho greater than meta. So this is the acidic character. Para is comparatively more acidic. Ortho is somewhat intermediate, and meta is